hopefully none of your friends and family have been affected by this London episode. And if they are, my condolences are with you. It was a pretty random event. I hope it doesn't affect you. All right. Today we're going to start on understanding linear programs. So we begin. So basic program for today's classes would be that we start with an example, a very simple example, and try to illustrate everything that linear programs can do. Try to solve them using Excel. And the reason this lecture is not yet online is because it's not completed. So there's going to be another bullet that will come below this one, which will be duality. We'll probably not get to it in the morning lecture, but we'll get to it in the afternoon lecture. And at the end of that, I'll put it online. So the program is just to look at a very simple example and try to see what we can do with linear programs. And then starting Tuesday, we'll look at more complicated models and apply it to financial applications. All right, so let's begin with a simple example. This is the so-called beer and ale example. So there's a beverage company that produces beers and ales. And in order to produce beer and ale, it needs corn and hops. There are all kinds of other requirements. Let's not worry about that for the moment. Let's just assume that currently it's only bothered about the limitations on production that comes from raw materials. And what this table says is that for every unit of beer, it could be a case, it could be a barrel, it could be several barrels, you get 13 units as profit. It uses 5 units of corn and 4 units of hops. Ale gives you 23 units of profit. It uses 15 units of corn, 4 units of hops. There are 480 units of corn that are available for you and 160 units of hops that are available. And the story, what this company wants to do is figure out how much beer and ale to produce that would maximize profit, subject to the constraints that it cannot use more than 480 units of corn and 160 units of hops. Very simple problem, and let's try to see how far can we push it, what kind of different ideas can we generate by just looking at this simple example. So in order to solve this problem, we're going to use decision variables xb, which is the amount of beer that I'm going to produce, xa, which is the amount of ale that I'm going to produce, or this company is going to produce. And the assumption that I'm going to be using is that xb and xa can be continuous, instead of it being discrete units, as is always the case in production. I'm going to assume that it's continuous. Now, given this, the objective value that I'm trying to maximize, bunch of typos that I will correct in the afternoon, is 13 times xb and 23 times xa. Where did I get those numbers from? They're just given up here in the table. Yeah. What? It has to be 13. Yeah, I said 13, but it's going to be corrected. So just when I was staring at it, one good thing is when I actually look at these in a big screen, I can see all my typos. But anyhow, it's actually a good thing that this came out to be 12. It introduces another issue that I'm going to talk about later. So think about it. This is 13 times xb and 23 times xa, and the constraints that I have is 5 times xb plus 15 times xa must be less than 480. That's simply coming from the requirement that I can't use more than 480 units of corn. 4 times xb plus 4 times xa should be less than 160. That should have been an xa. Which just comes from the fact that I can't use more than 160 units of hops. I cannot produce negative amounts of xb and xa, so xb and xa are non-negative. Those are my constraints. And if you put all of this together, you end up getting this optimization problem. You want to maximize the profit, which should have been 13 here, 13 xb plus 23 xa, subject to these two kinds of constraints, which are coming from the requirement that corn and hops cannot be more than what I have available, and non-negativity because I can't produce negative amounts. All right? So this kind of an optimization problem, and what's so special about this, in the next slide I'll talk about it a little bit more in detail, is called a linear program. Why a linear program? To define what a linear program is, let's go back to the definition of what linear functions are. So we'll call a function from Rn to R a linear function if it satisfies this property. If you take some weighted combinations of the vector x and y, so x and y are given vectors in Rn, alpha and beta are real numbers. So on the left-hand side, I'm evaluating this function at some weighted combination. On the right-hand side, I'm claiming that the function evaluated at this weighted combination is exactly equal to the weight alpha times the function at the vector x plus the same weight that's over here, beta, times the function at the vector y. If this is satisfied for all alpha beta and for all xy, then I'll call the function f linear. So linearity is sort of like saying things are on a straight line. If you put weighted combinations, you simply get the weighted combinations on the other side. And what this little derivation here says is that any linear function, so if f is a linear function, then you can always write, this implies that f of x can be written as A transpose x for some vector A. You can find the vector A. So given the function f, you can find the vector A such that f of x is always equal to A transpose x. And here's a little derivation that you can look at. So basically what you do is, because of this property, all you need to do is evaluate these functions at the basis vectors. So if you've got the function f of x, you can write that as f evaluated at this summation vector. What this summation is simply saying is represent the vector x as a summation of xi times the basis vector ei. And if you remember from last class, ei was this special vector which had zeros everywhere else and a 1 at the ith position. So what this summation is simply saying is that the vector x can always be written like this. Now I use the rule here. So I can pretend that xi's are my weights and ei's are the vectors. So what this rule tells me is that the function evaluated at that summation is exactly equal to the function evaluated at ei's multiplied by the xi's and added together. I'm just using the rule, the definition of linearity. Now I'm going to define that this number, whatever it is, let that be ai. Then this summation becomes ai times xi, which is the same thing as A transpose x. So this is sort of something to keep in mind, that if somebody calls a function linear, you should immediately think that it looks like that. Just A transpose x. Okay?
Sorry.
Yes.
What's an EI? I mean, I read through the notes yesterday also.
Yeah.
Could you define the vector?
Okay. EI is a vector which has 1 at the ith position and 0 everywhere else. So if I'm looking at, say, E2, the E2 vector would look like 0, 1, 0, 0 everywhere else. So in the second position, you have a 1. All right? So what that summation simply is saying, that if you've got a vector x which looks like this, x1, x2, x3, x4, let's say, you can always write this as x1 times the vector 1, 0, 0, 0, plus x2 times the vector 0, 1, 0, 0, plus x3 times the vector 0, 0, 1, 0, plus x4 times the vector 0, 0, 0, 1. That's all that summation is saying. This summation is simply saying that you can spread it out by using these vectors ei. Then the next part simply says, well, if it is this weighted combination, then evaluate the function here. That becomes f of E1, f of E2, f of E3, and f of E4. Right? So, and from there you can end up getting this. So from the point of view of what I want you to remember here is not so much the derivation. The derivation is pretty simple, and if you ever need to do it, you can do it. But what I want you to remember is anytime you have a linear function, that function would look like some vector times the vector x. All right? Okay. So we'll call something a linear equality if it looks like fx equal to b. So this is a linear equality if f is a linear function. So all linear equalities then look like A transpose x equal to b. So linear equalities always have the form some vector A transpose x is equal to some scalar b. So this is a vector. So let's, for the sake of notation, I'll put an underline every time I'm talking about vectors. So this is, in my notes, vectors would be boldface and scalars, or real numbers would be not a boldface, it's normal face, but on the board, underline would mean vectors and not underline means scalars. So that's a vector, and B is a scalar. So when you take an inner product of two vectors, you get a scalar. So this kind of equality is called a linear equality. A linear inequality would look like simply A transpose x less than equal to B, or A transpose x greater than equal to B. So for the most part in this course, unless otherwise stated, I would never talk about strict inequalities. When I talk about inequalities, I allow equality. Yes?
How do you define an inequality on vectors? How do you define an inequality?
These are all scalars. This B is a scalar. So anything underlined is a vector. But for now, so to answer your question, the way I'm going to define it is by component-wise. But right now, I'm just talking about scalar functions. It's a linear function from Rn to R. So I'm not going to worry about what happens to multiple dimensions right now. Okay? So we'll call an optimization problem a linear program if it has a linear objective function. The constraints are either linear equalities or linear inequalities, and it has continuous variables. All these three things have to be satisfied. If it doesn't have continuous variables, then it's not a linear program. And towards the last but one lecture, we'll talk about programs that satisfy these two conditions. It has a function that looks linear, and looks is important, and it has constraints that look linear, but the variables are not continuous. And for that, you need some other techniques. So if you go back to our example there, the objective function is a weighted combination of the decision variables xb and xa. So for this function, what is the vector A? That's just to keep ideas straight so that everybody, if I'm saying that the objective function looks like 13xa or xb plus 23xa, and I'm claiming that this is a linear function, and I've told you that a linear function looks like A transpose x. So if I want to write it in this form, A transpose x, what is the vector A here? 13 and 23. And the vector x is simply xb, xa. Correct. Right. So when you look at, when I'm saying that it looks like A transpose x, what it's doing, it's simply taking some weighted combination, A1 x1 plus A2 x2, and so on up through an xn. So anytime you see a function that looks like this, it takes the decision variables, multiplies them by some constants, and adds them up. That's a linear function. Every one of these functions looks linear. The objective is linear. The constraint here is linear. It's taking the decision variables and multiplying them by constants. The second one also is taking the decision variables and multiplying them by constants. Right? And therefore, this program here is a linear program. Okay. The next story, just a few notations before I go further. I will call a decision vector feasible if it satisfies all the constraints. So, if you go back to that example, over here, is this vector, let's just check some, let's just pick up some number, x vector equal to 40 and 65. So this means that this is xb, xa. Is this feasible? To check whether it's feasible, you just stick it into the constraints and see whether it satisfies both constraints. Just by staring at it, we know that it's going to violate the second constraint. 4 times xb plus 4 times xa must be less than equal to 160. So if you multiply, if you put these values in, you'll end up getting that 4 times 40 plus 4 times 65 is greater than 160, which means that this is not feasible. All right. Among the set of all feasible points, the points that maximize the objective value, in this particular case, since we're looking at a maximization problem, optimizes means maximizes in this case. So an optimal point is a feasible decision that optimizes the objective. There could be more than one. There could be more than one point which optimizes the objective. All of them will be called optimal decisions. Feasible are simply those that satisfy the constraints. Those are those that I can take, but they may not be the best decisions to make. Optimal are those that are best decisions to make. All right?
What do you mean by continuous variable?
Continuous variable. So typically, if I'm trying to model this problem realistically, I cannot say that xb takes values 3.7629, for example. So if I'm going to model this production problem, I really want my xb and xa to take only discrete set of values. I can make 23 cases or 24 cases. I can't make 23.5 cases. So when I say continuous variable, it means that xb and xa can take a whole continuous set of values. If they are not allowed to take a continuous set of values, the problem is not a linear program. The techniques that are used to solve linear programs cannot be used to solve those other problems. Okay. Why do we bother with linear programs at all? I mean, why do we care? We care because of two reasons. One, the geometry that you get from linear programs. And since in the last class we have talked about half spaces and hyperplanes. So what does a linear program look like? A linear program is simply a bunch of linear equalities and a bunch of linear inequalities. If I'm looking at the feasible region. Let's not worry about the optimal point for now. Let's just look at the feasible region. And a feasible region of a linear program is defined by a bunch of linear equalities and inequalities. When you have an equality, what does it do? It basically says that the whole feasible region should lie on a particular plane. That's what an equality says. All right. So if you take an intersection of equalities, all it will say is that this feasible region should sit in some affine space. If you don't know what affine space means, pretend you've never heard that term. But if you do, all the equalities are saying is that it goes and sits in some space which is not the entire space. It's defined by intersection of planes. Inequalities, on the other hand, give you bigger sets. It tells you that you should lie on one side of a hyperplane. So if you're looking at A transpose X equal to B, the inequality A transpose X less than equal to B is one side of this hyperplane. So if you take a bunch of inequalities, what you end up getting is that the feasible region of a linear program is an intersection of half spaces. So this inequality A1 transpose X greater than equal to B gives you this side, A2 transpose X greater than equal to B gives you the other side, and so on. When you put all of them together, you end up getting an intersection of the intersection of all these half spaces is something that looks like an object which has faces. So these are the faces of these objects and corners. Okay. Now the nice thing about having a structure like this is pretty much any set, any feasible region. This is some feasible region that I'm after. There's an optimization problem, I don't know what it is. But somehow I've defined that optimization problem can only consider decision variables that fall into this continuous set here. I can typically approximate that set very well by taking half spaces. So this outside box here is an approximation for the feasible set that has been generated by taking linear half spaces. And often, you can approximate a feasible region very well by half spaces. The moment you can approximate something by half spaces, you've got a feasible region that looks like this. So if you just look at L, the outside part, then that looks like this. The moment you have a feasible region that looks like this, and the objective is linear, you've got a linear program. So linear programs tend to give you a very good first approximation. They're not necessarily exact, because this point, for example, is not feasible. You can never take this decision because it's outside the feasible region. But perhaps you can move it back somehow, approximate somehow. So the one reason why we worry about linear programs is that they give you a very good approximation. But if that's all there was to it, then we would not have worried about linear programs at all. The other important reason why we talk about linear programs is they can be solved very efficiently. These are programs, you can give them very large numbers. I don't know, many of you might be aware of this company called SAS, which produces data management software. So their solver can solve linear programs which have about 2 million variables.
What about Cplex?
Cplex is good, but it doesn't do it for particular structured problems. In financial applications, SAS is slightly better. Cplex is good for more logistics applications. So Cplex is another solver, which is if you are an OR person, it would be sacrilegious to say that SAS is better than Cplex. So anyhow, I mean, Cplex is also a big solver. But the thing to remember here is there are two reasons we worry about LPs, and the two reasons is they are good approximations. You need something to be a good approximation, otherwise it's no point worrying about it. And the other reason is that you can solve very large problems. Often it's better, if you're going to solve a problem that looks like this, which is basically a nonlinear optimization problem, and we'll come to it later on, it's often better to approximate it by a much larger LP, solve it, and get your solution. If you have some nice structures, then you can solve the nonlinear program directly, and that's what we'll discuss later on, once special structures can be solved. Okay. Now let's go back to our problem, and let's try to see how does one solve LPs. So before doing that, let me tell you how I got this set over there, and also give you an exercise in to look at feasible regions of LPs. So the problem that I've been talking about, I might as well put it in a corner here because I'll come back to it over and over again. Oh, here it is. So the constraints were 5 times xb plus 15 times xa is less than equal to 480. 4 times xb plus 4 times xa is less than equal to 160. xb and xa are greater than equal to 0. And I want to maximize 13 times xb plus 23 times xa. All right. So let's look at the feasible region of this problem. So on the axis down here, it's xb. Axis up here, it's xa. So first of all, the constraints xb and xa non-negative means the feasible region falls in this quadrant, in the positive quadrant. This constraint, 4xb plus 4xa is less than or equal to 160, says what? Here's 40, and here's another 40. So it says, so here's the vector 4, 4, and transpose x is, so this equality here is simply, let's not put an equality there. So this line here is the vector 4, 4, transpose x is equal to 160. This side, you have 4, 4, transpose x is less than or equal to 160. All All right. So if you just look at these two constraints and that constraint, you end up getting that the feasible region is this triangle. Everything that's in here is feasible. Now you add the last constraint over there, and that will give you 32 here, and divided by 5, that's 96. So 80, somewhere over there. So let's just deem here, that's 96. So now the feasible region is this space. Right? And this point here turns out to be 12 and 28. This point here is 40, 0. This point is 0, 32, and 0, 0. Right? So that's what I meant by saying that if you look at the feasible space of a linear program, you always end up getting a set which looks like this, multidimensional. In this case, it's 2D. In 3D, you'll end up getting, instead of lines, you'll have planes here. But these are faces that meet at points. In multi-dimensions, instead of just having points and lines, you'll have planes, lines, and points. But they all look as if the most important thing that you should remember is that it has corners and faces. And those corners and faces will play an important role. All right. So we found the feasible region of an LP. Now let's try to find out what is the optimal point here. And how does one do that? Okay. So today I don't have a watch. So at some point just warn me if I'm going way over. What?
It's mentioned there, it's at 10:27.
Ah, okay. Very good. Thank you. My watch was saying 9:48. All right. So we figured out where the feasible region is, and now what we want to do is do this. Maximize this quantity, this weighted combination of xb and xa over this feasible region. All right? And the way we're going to do it is we're going to say that if I pick any, let's look at blues here. If I pick up any value z, so z is a scalar value, and I look at points which satisfy this. 13 times xp plus 23 times xa. What do these sets of points look like? So take z to some fixed value. If it confuses you, let's call z here to be some number. I don't like numbers, so I'm just going to put something here, 72. Who cares what that is? But let's say for some fixed number, what does this set of points look like? It's a line. In multi-dimensions, it's a hyperplane. Let's say that, and what kind of a line is it? Can you say something more about that line?
With a slope of minus 23 or something.
It's a slope of minus 23 about divided by 13, but rather than looking at that slope, what I want to look at it, it's perpendicular to the vector p. Same thing. It's just that in multi-dimensions, talking about slopes become tougher than saying that a line is perpendicular to a vector, or a plane is perpendicular to a vector. That's easier to say, or easier to think about, rather than talking in terms of slopes. All right? So in 2D, it doesn't really matter. It's the same thing. So let's say that that line, so here's the vector that I'm trying to optimize. That's 13, 23. So for any given value of z, that would look like a line perpendicular to this vector. So maybe this is that line. Z is equal to 72 gives you a line here. All right? Now, one way of trying to optimize this thing is to keep increasing the value of z. Right? I'm trying to maximize this quantity over this feasible region. So one way I'm going to do it is I'm going to take this line and move it parallel to itself. If I keep moving it parallel to itself, it's going to remain perpendicular to this vector p, the profit vector. So let's call this vector the profit vector p. And I'm going to do that until I end up leaving the feasible set. I can only remain in the feasible set Therefore, I can optimize this thing conceptually. This is not an algorithm. This is not something that you can do in more than 2D, or at least I can't do it in more than 2D. But at least it gives me some idea of how to go about finding an algorithm. So I'm going to take this line and I'm going to move it. And if my drawing is correct, which will be the optimum point?
1228.
1228. So this will become the optimum point because I move it up. And that's the maximum value. This is the highest I can push it. Okay. So that's what's being shown in this picture. The gray area here is the feasible region, which is this feasible region here. These lines here are lines that are perpendicular to the vector P, and I'm moving them up until I start leaving the region. And the moment I leave the region, it's right at the boundary that I get the optimum point. So if this is the algorithm, or this is the idea, then what are the points that can be optimum for a linear program? The corner points. This point, for example, can never be optimal, right? Is it possible that this entire line is optimal?
Yes.
Yes. So it's not necessarily the corner points. The optimum point would be a boundary point, but not necessarily a corner point. In order for this entire face to be optimum, you need to have a vector P which sort of looks like that. Let's call this some vector P tilde. You can find the vector P tilde such that an entire face becomes optimal. But what we know is even if an entire face is optimal, you can find a corner that is optimal. This is what I call a corner. I haven't defined to you what algebraically a corner is, but at least on the picture, you would agree if I call this a corner. That's a face. The entire face can sometimes be optimal. A corner can be optimal. And another thing that can happen, which won't happen in this LP, and typically will not happen in any kind of production type LP, is that the problem might be unbounded. So if the feasible region is like this, the feasible region is bounded, and therefore the problem can never be unbounded. The X A and XB that are allowed to be feasible cannot be very large because they have to sit in this set, and therefore the function evaluated at that point cannot be very large. But it's possible that a feasible set looks something like that. So this is an unbounded set. I should move to my black pen. And so it is possible that you get an unbounded optimum value. Typically it won't happen. Now, maybe later this afternoon or definitely on Tuesday, we will see how LPs can be used to find arbitrage opportunities. And there, you are looking for unbounded LPs. If you have an arbitrage opportunity, for those of you who know what an arbitrage is, you can make infinite amount of money, which means that the optimum value must be unbounded. And yes, question.
How did you get the vector P? I mean,
Vector, which vector?
P.
P.
Yeah. And in
From here.
the unbounded case?
Oh, in the unbounded case, here's the vector P. So if you take any vector P that's in this direction, the problem will become unbounded. I'm not saying that this is happening in this example. I'm just making up a feasible region.
No, since you're saying that the optimum could be on the line as well.
Yes.
So it's not necessary that P will be perpendicular to the line, the other line.
No. Okay, let me back off. What I was saying, we first looked at this particular case that we have, which is maximizing this. For that particular case, we have resolved that this point, 1228, is optimal. But now I'm thinking that suppose I give you the feasible region and I ask you, what are the points that can be optimal for some P? So the question is, can this point be ever optimal? For any P in the world, can this point be optimal? No. Because no matter what P is, I can always slide it somewhat more in the direction of P. But it is possible that this entire phase is optimum for some P, and here's the example. For this P tilde, this entire line is going to be optimum.
This is for case basis.
This is a case-based analysis, right? So what I wanted to point out was basically that these four things can happen. Optimum point is always at the boundary. If the optimum point is unique, if there is a single point that is optimum, then it must be a corner. An entire phase can be optimum, but then there is an optimum corner. And the problem might get unbounded or infeasible. Infeasible means this feasible set is empty. There are no points that satisfy all the constraints. Okay? So those are the four things that can happen. So if I want to construct an algorithm for solving a linear program, what do I need? I'm going to need some definition of a corner. Looking at this, all these four cases, I figured out that, all right, corners are the only thing that I care about. Everything else is useless for me. Because if there is an optimum point, I can find it at a corner. I'm only interested in optimizing. Let's just get a corner. So the rudimentary algorithm that I'm going to be using to try to optimize linear programs would be to find a corner. In a picture, I can tell you what a corner is, but typically pictures are useless after 3 dimensions. So I need to tell you algebraically some way of mechanically telling you, okay, this point is a corner, that point is not. On a picture, I can tell you this point is not a corner, that point is a corner. This point here is not a corner. I need to have some algebraic way of defining what a corner is. And then what this algorithm will do is somehow it will get itself to a corner. In this particular problem, the easiest corner is here. 0, 0. It's a corner that can be found very easily. And then I'm going to hop from this corner to a better corner. I'm going to have to figure out how do I go from one corner to a better corner. And also, and which is something that will not happen in this problem, is I have to figure out when is this problem unbounded. Because if the problem is unbounded, it is possible to keep getting better and better and better corners, and you will keep on going forever. So at some point you have to stop and say, well, I can't keep on going forever in this problem, and therefore I'm going to stop right now. So those are the things that I need to do for an algorithm. And I'll start looking at an algorithm momentarily, but one thing that I want to focus on before we leave this topic, and it's better to do it geometrically, is an issue that is important later on. So right now the vector is, let me just redraw this picture. So this is my point 1228, which is optimum. And I'm going to put my p vector here. This is just a vector 1323. So here's the line that's perpendicular to this vector. So now let's ask ourselves, at this point, is there a range if I change my p such that this point will still remain optimum?
Mm-hmm.
Yes?
Yes.
So how would I find that range? For example, so in this particular case, let me just tell you how to find that range. You take a perpendicular to this face, so this is 90 degrees. Take the perpendicular to that face, so that is 90 degrees. Let's call this P1, call this P2. So as long as the vector P lies in this cone between the vector P1 to the vector P2, this point is optimum. Right? Think about it. If it's over here, this entire face is optimum, but that point still remains optimum. If it's over here, then this entire face is optimum, but that point still remains optimum. If it's somewhere in between there, then that is the unique optimum. But what happens if it comes over here? Let's use a different color. So what if this is the vector P? What point is optimum now?
0, 32.
So this is the optimum point then. And on the other side, point becomes optimal.
96.
96 is infeasible.
Yeah, okay.
So that 96 will not be optimum, it will be this point which is going to be optimum. Correct? Okay. So from this little exercise that I laid out here, two things I want you to remember. One, in the event that there is a unique optimum, typically there is a range of P for which that point still remains optimum. You could be unlucky and your P might be equal to P2, in which case, ever so slightly if you move the vector, the optimum point will jump very far away. Right? So if you look, if the P vector was equal to this vector, then if you move it in that direction, you still remain here at the optimum point. If you move it in the other direction, then you jump over here. In practical applications of optimization, this particular point is very important. Typically, these numbers that I put here are something that are estimated from some kind of historical data. Who knows whether you're going to make 13 units of profit out of a beer case on 23 out of ale or not? Typically what you'd end up getting is a range. You're going to say, well, the profit is going to lie somewhere in the range 13 to maybe 17. And the other one is going to lie between 19 and 24. You typically don't have a value which says, yes, this is the exact number that's going to be there. And therefore, if you have an optimization problem which is extremely sensitive to the numbers that you stick in there, it's typically a useless optimization problem. You don't really want the optimization problem to be too sensitive. And that is a problem that's there with linear programs. If it happens to be in this cone, then moving it slightly will not make any difference. You will still make that point as the decision. But if you move it more than that cone, then you will jump very far away. You'll jump from that point to that point, or that point to this point. So there is this sensitivity that's there in linear programs which can make things unstable. And very recently there have been some techniques generated called robust optimization. And what they do is instead, so the reason this causes a problem is because there are corners. So robust optimization would say, well, just round these corners. Who cares about whether you move it slightly or not? Just round them. And now if you do the optimization, things will never jump very far away. They'll gracefully move. That's something to remember. In this class, we will not deal with all of that. But it's something that keep in mind that if you're ever using things in practice with linear programs, things are unstable, and you have to be careful about it. The other fact is, which we'll be using later on today, is the fact that if you move it slightly in this cone, that will remain optimal. And we'll use that to define duality later on. All right. So what do we know so far about linear programs? They're defined as such: linear objective, linear constraints. This is also a linear constraint. It just looks special because both variables are not there. A feasible set of a linear program looks like this quantity over here, an object with planes and corners. And we have a hypothetical way of doing it, way of optimizing a linear program, which is taking this hyperplane and moving it parallel to itself until we hit a corner. Okay, so now let's try to make this into a bona fide algorithm. So in order to make it into an algorithm, what I need to tell you is what is a corner. So in order to define what a corner is, I need to tell you some quantity called an active or binding constraint. And we'll come back to this story of active and binding constraints when we talk about duality. So we'll call a constraint A transpose X active or binding at a point X bar if this constraint has been satisfied as an equality at that point. All right? So, for example, if you take a point here, if you take this feasible point, let's call that X bar. So at this point, what are the active constraints? So in this particular LP, you have 4 constraints. You have 5xb plus 15xa less than or equal to 480, 4xb plus 4xa less than 160, xb is greater than or equal to 0, and xa is greater than or equal to 0. So at this point, what are the active constraints? Only the second one. So the active constraint is simply 4xb plus 4xa is equal to 160. All the other 3 constraints are inactive. This is strictly less than 480, xp is strictly positive, and xa is strictly positive. How about here? If this was the point x bar, what are the active constraints there? So at this point, the constraints that are active are xa equal to 0 and xb equal to 0. How about at this point? Here you have the active constraint as xa equal to 0, and then you have the other active constraint, which is 5xb plus 15xa is equal to 480. So those are the two constraints that are active at that point. So if you just keep looking at this, it tells you that the one way of differentiating whether a point is a corner or not is to look at the number of active constraints at that point. This fellow is a corner. It has got two active constraints. This fellow is not a corner. It's got one active constraint. How about a point here? 0. No active constraints. It's an empty set. Whereas every corner you can find two active constraints. Why 2? Because this is a problem in R2. So the definition of a corner is that a point x bar is a corner if it is the unique solution of all the binding constraints. And if you want a unique solution of a bunch of constraints, and you're talking about a problem in R2, you need to have two constraints. You've got a vector in R2, it has got two unknown variables, and you want a unique solution to a bunch of equalities. And the only way you can get it is that you have exactly the same number of equality as there are variables. So for every corner in R2, you need to find two active constraints. There are 4 of them. So if I pick any two constraints and make them active, will I get a corner? Yes? No? Maybe? It may not be feasible. So a corner is a point that satisfies exactly two active constraints, but if you arbitrarily pick two active constraints and claim that that should be a corner, it may not be feasible. Take this point, 96. What are the constraints that are active over here? Xa equal to 0, and the other one is 5xb plus 15xa is equal to 480. There are two constraints that are active at that point, but that is not a corner. Right? Because it violates some other constraints. So finding corners is a little bit tough because I have to kind of search through all sets of points where two constraints are active, but they must all satisfy every other constraint that are there in the problem. If somehow I could say, and I pick any two constraints and solve for it and I get a corner, then I'll be in a happy situation. The problem is that that's not true. We'll have to figure out some way of doing it. Typically, in all kinds of problems that involve some kind of investment, some kind of production, and things of that sort, 0 is our favorite corner. Don't do anything, you don't get anything. So, I mean, that's a point where everything is good. You've got n constraints, you've got a variable, and for every variable, you're setting it equal to 0. So, typically, in the kind of problems that we'll be interested in, finding one corner is going to be easy because I'm going to take it to be 0. But in other problems, this is not the case. You cannot find a favorite corner, and trying to find a corner is a bit tough. Because of this fact that if you take any two active constraint, you might end up getting an infeasible point, and so you might have to cycle through it, keep cycling through constraints until you get a point which satisfies active constraints and is feasible. All right? So for now, let's say we have our favorite corner, and let's not worry about it. So here are the 4 corners for this point. At corner A, you have 0, 0 active. At corner B, you have 4xb plus 4xa equal to 160 active. And this is what happens when you cut and paste. You make one error and perpetuate it everywhere. And you have a constraint xa equal to 0. In that corner over there, you have the constraint 4xb plus 4xa equal to 160 and 5xb plus 15xa equal to 480. And the last one, D, you have xb equal to 0 and the other constraint is type. So currently, what we have done is I'm going to start with my favorite corner, which is this one. And I'm going to try to see whether I can move from this corner to a better corner. Question?
We can have 3 constraints active at a corner also in this.
Yes, you can have it, but it's usually a very delicate situation. You perturb anything ever so slightly, it won't happen. So one thing to remember with LPs is that you can have 3 constraints active at a point, but you take an epsilon and change those numbers by an epsilon. Only 2 will be active at a point. So it has to be matched exactly. The constraints have to sort of be, the rank has to be less than the full one. Otherwise you won't get it. And you perturb ever so slightly any constraint, the rank drops. And then you won't have this situation. So generically speaking, at a corner you'll have exactly 2 that are tight. But if you remember what I wrote up there, I did not define a corner by saying how many were binding. I simply said that it must be the unique solution. So the methodology that I'm telling you is a way of finding corners, not the definition of a corner. And there are pathologies in which case you have to be careful about what happens. I mean, I don't really have the time in this course to go into all the details, but if you're really interested, I'd be very happy to tell you offline what's happening. So here, what we want to basically give you is an idea of how these things are optimized, and really tell you more about the pitfalls that you have to keep in mind when you get a solution. We will not really be solving. We will never write an LP solver. We'll defer to our favorite Excel to solve it. All we want to know is that if it gives me a garbage answer, I need to be able to detect that it's a garbage answer. And if it's a garbage answer, what can I do to improve it? That's sort of the idea. If I decide to start writing an LP code, we'll have to have an entire course on LP. And I don't think I can do it in 6 weeks. So if you're really interested if you're somebody who wants to talk about how to design LP codes, I'll be very happy to talk to you offline and we can talk about all the various issues that happen. All right.
This first condition over there,
Which one?
2 unknowns and for 2 binding constraints, we'll have to scroll a little.
Which one?
We'll have to scroll down.
Yeah.
Is that there to just maintain that you get a feasible kind of a solution?
No. It may not be feasible. So what I'm trying to say is that if you look at any 2 binding constraints, you may not get a feasible point. That's an example here. This is a point which has 2 binding constraints. It's not feasible. But at every corner, you must have 2 binding constraints, at least 2 binding constraints. So it goes one way, that corner means binding constraints, but binding constraint doesn't mean corner, and that's the problem. If it meant both ways, then I would be very happy. Right? Okay. So once we figure out what a corner is, let's just see how we're going to solve this problem. And the way we're going to solve this problem is going to start from a corner and then move to a better corner. And our favorite corner is corner A, which is 0. So from here, we'll try to move towards corner B, which is this corner. So here is my corner B, A, that's corner C, and here's corner D. So if I move towards corner A, this is the direction I'm moving, what happens? XB increases from 0. This is the XB dimension. It increases from 0, and XA is equal to 0. It stays at 0. XA is equal to 0 here. Along this face, XA remains at 0. And therefore, if I see what happens to the objective function, I check the change in the objective function with respect to this movement. The objective function is 13xb plus 23xa. dxa is 0, so this drops out. dxb is positive, so we end up getting the change in the objective function is 13 times dxb, which is positive. And therefore, by moving in this direction, moving from this corner to this adjacent corner, I will improve the objective function. So I'll keep moving, and I move to this corner. Now, so one of the issues, again, is that, so far we've figured out how to get a corner. We can get that corner by looking at tight equations. Now I'm telling you, what I want to do is move from one corner to an adjacent corner. This is an adjacent corner. That is an adjacent corner. This is not an adjacent corner. Now, I'll tell you the answer in the next slide of how to do that algebraically. So I just keep thinking about what differentiates this corner from that corner versus that corner from that corner. What's the difference? There is some difference between going to this one versus going to that one. And when we are solving LPs, we don't like going through here. That's also not an accurate statement because most of the recent advanced ones actually do not like going around. They like going there. So why waste the time of going around if you can go across?
So we can move along one constraint to reach the other corner, whereas we'll have to move across two constraints to reach the non-adjacent corner.
Right. So that's the difference between this point and that point. Now, how can we make that into an algebraic thing? Keep thinking that, and then we'll come to it in a moment. Okay. So we move to point B. At point B, now I have two adjacent corners. Either I can go back to A, or I can go to C. Going back to A wouldn't help me, because I just came from A. But what if I move to B? If I move to B, what happens? XB reduces, so because now I'm moving backwards in the direction of B, so XB is negative, but I have that 4 times the change in XA plus 4 times the change in XB is equal to 0. Why? Because I'm sitting on this constraint. This constraint here is 4XB plus 4XA is equal to 160. If I'm sitting on that constraint and I'm moving along here, then I must have that the change is 0, because I'm always on that constraint. So what does that tell me? That tells me that I can write the change in the objective function as just a function of dxb in this particular case. So what is the change? It's 13xb dxb plus 23 dxa. If you plug in that, you'll end up getting minus 10 times dxb. But remember, dxb is negative, so you end up getting minus 10 dxb is positive. Okay? dxb is xb is reducing. So if the change in the objective function is minus 10 times dxb, it means that I'm improving. So I come and get stuck over here now. I'm in corner C. One thing, so two things to remember here. I have to figure out how to move from a corner to something called an adjacent corner. But if I figured out how to go to an adjacent corner, finding out what happens to the objective is going to be very easy. I can just quickly say whether I'm going to improve or not improve. I don't have to go check that corner. Just by pretending to move in that direction, I know what to do. Question?
So will it be moving like this or this way? Because in this direction that is 23xa. So the the same change in xa will improve the objective function more if we move in that direction.
Perfect.
So shouldn't we should move like this and then that, like
right. All I'm trying to say is that it doesn't really matter which one you choose. So this is not the optimum algorithm. All I'm saying is what I'm trying to point out by doing this step. You're absolutely right. I should have gone here and there rather than going there and there. It turns out that the greedy algorithm, this is sort of like a greedy algorithm. Every step you want to make the maximum possible gain that you can get. Can work sometimes and can fail sometimes. Doesn't really matter. And you're absolutely right, in this particular case, I might have as well done that than doing this. But the point that I want you to take away from this exercise here is simply that if I go to adjacent corners, I have a very nice expression for what happens to the objective. It's simple expression. I don't have multiple variables to worry about. I just have one variable that's going to change. And just by looking at what happens to the sign of that thing, I know whether I want to go there or I don't want to go there. And that's why going from corner to corner is nice. Because I don't really have to go there. I don't really have to check that point. I can just sit at a point and say, will I go there or not? But what I don't really know still is in the picture I can tell you how this works, but what happens when you can't draw a picture? Okay, so you come to corner C, and then at corner C, you can again think of going to the adjacent corners, which is either going back to B, which doesn't make any sense, or going to corner D. So if you go to corner D, what happens? You have dxb less than 0, and you have 5 times dxb plus 15 times dxa equal to 0, because this constraint is tight. So along this constraint, you should have that the change in the two variables is 0. Solve this, you end up getting that dxa is equal to minus a third times dxb. Put it into the change in the objective function, you end up getting that the change in the objective function is 13 minus 23 divided by 3 times dxb. Whatever this quantity is, it's less than 8. So 13 minus 8 is positive. dxb, remember, is negative. So you end up getting that the change in the objective function is negative, which means that you won't go to corner B. You won't go to corner B. So what do? Stay at corner C. Now, geometrically, we found that corner C was optimal. But how can one argue? Now, don't get fooled by these pictures. Pictures can sometimes make you believe things that are not universally true. But if you're sitting at this point, at a corner, and you look at all your adjacent corners and say, I'm not going to go to any of those adjacent corners. Is it possible that there is a corner somewhere far away, not adjacent, which is better than the corner that I'm sitting at?
Yes.
Yes.
Is it possible?
Yes.
If it's possible, then I'm dead. Linear programming doesn't work. So I would claim that it is not possible. It is not possible that there is another corner which is better if you have found that the adjacent corners are worse. Now let's try to figure out why this is true. This is very special about linear programming. So just to clean up the story here, let's get rid of all of this extraneous junk. It all comes from the geometry. And as long as you keep this in mind, the details of the algorithms are not really relevant. So I'm sitting at this corner, my corner C. Here's my corner D on this side. And let's just make our life a little complicated and say that the feasible region looks like this. So let's just change the feasible region a little bit. And let's say the LP feasible region looks like this. And for some reason, I have concluded the C is optimum corner. And at that point, I know that I don't want to go here. I don't want to go there. Is it possible that this might be better? Let's call it corner E, corner F. Do I have to check E and F?
No.
Because if I have to check E and F, then this method will fail. Because the reason this whole algorithm works is because if you go to an adjacent corner, computing that is easy. I have to just look at the direction and see what happens. So somebody said, no, I don't have to consider E and F. Yes, why not?
Because it's a convex feasible region.
So what?
And it's a maximization problem. So if it was...
It's a convex feasible region, it's a maximization problem. This could be optimal.
It will not be...
Because the objective function is linear, it will either move in one direction or the other. It won't sort of go up and down.
Well, okay, so the thing that you guys are, it's sort of right, but I can give you a pathological condition where it will happen. Think about the case where this entire thing is optimum. It's possible. But that being aside, I want a little bit more concrete. So what you're basically saying, so the question that I'm asking is different from the question that you are answering. The question that you are answering is, if this point is optimal, can this be optimal? And the answer that you're saying is no. The question that I'm asking is, all I have decided at this point is going here and going here is not optimal. That's all I know. When I come and sit at this corner, the only thing I know is that if I go to the next two corners, I cannot do better. At this point, at corner C, corner B is not good, corner D is not good. Now the question is it possible that I would improve by going F and E? That's the question. So I do not know whether C is optimal. I'm thinking, or maybe I should put a question mark over there. All I have found out so far is if I reach C and the two adjacent corners are not optimal, I want to say C is optimal. But I can't say that unless I say that I don't have to worry about E and F. Why not?
Because we were moving perpendicular to that vector P. So
Which vector B?
P, you were thinking.
No. We are not moving perpendicular to any vector P. That picture is gone. That's only something that will work in 2D. So right now I'm using my algorithm, which is jumping from corner to corner. And all that algorithm knows when it has arrived at point C is that I cannot go to a better adjacent corner. That's all it knows. So now it wants to know is if I hop 2 corners, can I get to something better?
You can't, because I mean to reach E or F, you have to pass through that feasible region.
I have to go like that.
Yeah, and
Right.
that none of those points are open, and the value of the objective function is lower than in the region around.
We don't know that. We don't know that the value of the objective function is lower. All we know is in this direction the value of the objective function is lower, and we know that in this direction the value of the objective function is lower. That's all we know.
Because
Yes.
because E and F are linear combinations of these 2 points,
Yeah, these 2 directions.
these 2 directions.
Correct.
And that the objective function is linear, so if we're going down both ways, then we're going down any linear combination of these
Correct.
2 directions.
That was the fact that we wanted to. So all of you approximately have the idea, and this is the exact answer, which is if I sit at this point, and to put it very technically, if you sit at this point, the entire feasible region lies in the cone generated by the vectors from the 2 corners. What is a cone? So whatever be the feasible region, I don't really know what the feasible region is, and I don't care. All I know is that the feasible region would lie in this set. I'm just looking at the constraints that are sitting at the corner C. Whatever be the feasible region, I don't care whether there are corners here or not corners, who cares what there is. I just know that it's going to lie in this side of this vector and that vector. So any direction that I move here, let's call this delta x or something, I can write that as some mu times that direction. Let's call it the direction from C to D. X, my notations are all screwed up. Let's call it y times CD plus mu2 times y CB, where mu1 and mu2 are greater than or equal to 0, because at the boundaries it could be 0. And therefore, if I look at what happens to the objective function in this direction, you end up getting it's mu1 times P transpose y CD plus mu2 times P transpose y CB. Both of these are negative because I've found that my current corner is optimum, which means that no matter where I go, this summation would be negative, less than or equal to 0. And therefore, there's no point in going anywhere else. So that's something very peculiar and nice about linear programs. And the reason it works is because the objective function is linear and the constraints are linear. If the constraints were non-linear, you would have a problem. You may not be able to conclude that the feasible region lies here. You can refine it by saying, well, if it has this property, it can do it, and so on. But when you have these 2 things, the very nice thing that happens is you sit at a corner, just look at the adjacent corners and say, well, if those are not good, nobody else is good.
Can you explain this again?
Okay. So I'm sitting here, and I've checked that this corner and that corner is bad. Now the next step the geometrical fact that I'm going to use is the fact that if this is a linear program, then the entire feasible region of this linear program will lie in this cone that is generated by just the constraints that are sitting tight at that point, right? And I have gone along this tight constraint and I have gone along that tight constraint and said that going in that direction is bad. So which means that if I go from C to D, the change in my objective function is negative. If I go from, this is probably not at all visible from back there, so nobody's complaining, which is good. So let me write it up somewhere else. So I have concluded that if I go from C to D, then the change in my objective function is less than 0. If I go from C to B, then I get a change in the objective function which is less than 0. These are the 2 things I know. Now I claim that any direction here, any delta x, any change can be written as some positive times ycd plus some positive number times y CB. Just looking at this picture, I can represent this vector by taking its component down here and a component down there. So it's a non-negative combination. So the change in the objective value, if I go in this direction, is going to be equal to mu1 times P transpose y CD plus mu2 times P transpose y CB. This and that is negative, which means this total thing is negative, or less than equal to 0. And therefore, I need not move in any of these directions. I don't have to worry about it. And to get to one of these corners, I must go through a direction that belongs in this corner. And going in that direction is useless for me. So if I just check the extreme directions, I'm okay. All right? Yeah.
Just assume that the corner 0, 0 is not on the feasible points.
Yeah.
And like this. And how do we know from which point we have to start?
You don't.
Oh, we don't.
You don't.
Okay.
This is what I was saying, that in the kind of problems that we are talking about, we would be lucky because we would know that 0, 0 is good. So in all kinds of production type problems where you're trying to produce something, typically what happens is 0 is feasible. It's typically feasible not to do anything, and which means 0. But if 0 is not feasible, then you've got this problem. How do you get the first corner? I don't know whether I wrote that down here, but I might have actually. Well, okay. So getting the first corner is tough. And actually, in order to get the first corner, what you have to do is solve another linear program, which is in the language of linear programming that's called a phase 1 linear program. You solve a linear program to get your corner. And you get the corner, then you go and really solve the linear program that you're interested in.
We can't choose it randomly?
Yes, but as the dimension increases, choosing it randomly will become very inefficient. Because basically, the question is how do you get the corner? You randomly pick tight constraints, solve for them, and see whether it's feasible. Right? So if the number of variables is large and the number of constraints are small, trying to find that random collection which will be feasible will turn out to be a problem. And there's no systematic way of doing it. So the systematic way that people go about doing it is to set up another linear program which looks at infeasibilities. And now say, try to minimize the infeasibilities. And if you can minimize the infeasibility to 0, it means you've got a feasible point. And for that, the point 0 will be feasible for that LP. So you start from an LP for which 0 is feasible, you move to another point, and from there you jump over to the LP that you want to solve. So it's a tough problem, but it's doable. And it doesn't give you any new intuition, so I don't want to worry about it. Yes?
What happens if you have two unique solutions which are not adjacent?
Cannot happen. Think about it. Why can't it happen? So is it possible that both this corner, so first of all, that both this corner and that corner are optimum? Or let's say this corner and that corner is optimum. What will happen to the points in between? They must be optimum because it's linear. You function, so linearity gives you all kinds of beautiful properties. Life becomes infinitely easier because this could have happened if the function was not linear. You could have 2 points which are optimum, and everything in between is not optimum. But in linear problems, it will not happen. It cannot happen. And if this entire line is optimum, what can you say about a point here? If I tell you that this line is optimum, what about this point?
Not up.
Not optimum?
It depends if it is in that phase.
Yes, so I'm telling you, you're going into the feasible region of the phase. And it's not a phase, it's an interior line.
But an interior line cannot be optimal.
It can be optimal. The entire vector could be completely perpendicular to this entire. Remember, we have thrown out all linear equalities when we do these kinds of things. We are drawing the picture of only equalities. It's possible that the objective vector is completely orthogonal to this feasible region, in which case everything could be optimal. So if it so happens that an interior line is optimum for some reason, if I just give you this condition that this line is optimum,
Can an interior line
then
be
everything is optimum.
Can it be optimum in an LP?
Of course it will. Take the zero vector as the objective. Everything is optimum. You can always get, any face can be optimum, and the full face is also a face. Everything can be optimum. And if you take it multi-dimension, then you don't have to take zero. You could take some other vector. We basically take a vector perpendicular to this thing, and then that will make it the entire thing optimum. There was another question somewhere here. No? Okay.
So,
Yes.
one question. I mean, can't we have a feasible region like this?
Good question. So the question that was asked is, could we have a feasible region like that? Is it possible for an LP to have a feasible region like that?
No, that's not possible.
Not possible. Why?
Because you have linear inequality, you end up with a convex region.
Well, convex, but more special than convex. It's not just convex, it's even more special than convex. Convexity is using less properties of linear programming. So the reason this won't work is because in a linear program what you have to do is set up linear inequality. You can say it lies on this side, it lies on that side, it lies on this side, and it lies on this side, and you end up getting a feasible region which is just this. In an LP, all you can say is that you've got linear inequalities and linear equalities. You can only be on one side of a linear equality. So if you just say that you're going to be one side of the other, you'll end up getting that diamond as the feasible region. All right? Okay. Let me actually finish up with this. Let me just preview this, and then we'll get back to it again. So one of the things that, one of the problems that we are facing, yes.
You say it's more special than convex.
Yes.
What is that more special?
I didn't want to talk about this right now because people don't know what a convex set is. So, for example, for those of you who do know convexity, let me just tell you, but those of you who don't, we'll get to it when we do nonlinear programming. So this is a convex set. Describing this convex set is a lot harder than describing this convex set. Because this convex set, all I need to know is these 5 points, and any point that's in the set, I can just describe it completely. So this convex set, I can't do that. So the fact that an LP's feasible region looks like this gives me more power than just knowing that it does that. So it's more special, which means that I can maybe use it for optimization. Okay, so the last thing, I just want to take 2 minutes and then I'll let you go, is that we will come back and start looking at LPs which have this special structure, which has only non-negative variables and all constraints are equalities. And the reason we like this kind of a structure is because defining adjacent corners for this guy is good. I can define it very easily, so I can algebraically move from one to the other. And I'll leave you with this thing that this is the LP that we are interested in. This can be converted into the standard form by putting new variables here. So what I'm doing is I'm adding a variable here, SC, and insisting that be greater than or equal to 0. If SC is greater than or equal to 0, that means that 5xb plus 15xa is actually less than or equal to 480. That's what I want here. Here, I put another slack variable, that's why the name S is sitting here, and set that is greater than or equal to 0. This makes sure that 4xb plus 4xa is less than or equal to 160. In the objective, I just put a 0 objective for SC and SH, so that doesn't affect what happens to XB and XA. So this is the LP that I started with. This is a new LP that I have created, where there are only non-negative variables, and all constraints are equal. So by saying that I'm only going to look at LPs that look like this, I'm not restricting myself. I can convert any LP into this form. All right, so I'll just stop here and then we'll go back to SLP in the afternoon.